All of you can see my screen?
Yes, sir.
Yes,
Yes, sir.
Yes, sir.
So I am at slide number 43.
42, 43.
Okay, the 43. Yes, sir, 43.
Yes, sir.
Okay. So till now I was discussing about the generation aspect of our Indian power system. Now let us discuss something about the demand side also. And because demand side is also very peculiar due to the change in weather condition, due to the change in different regions have different type of load, and on a daily basis there is also a typical profile. Okay, morning and
Sir,
evening.
sir,
Yeah.
can you put it on slideshow, sir? Because we are missing some information at the bottom of the each slide. That's why.
Madam, it
Slides.
is in slide mode only.
No, sir. In the slideshow mode, if you go, okay, we have the slideshow here in the main menu. So if you go there and if it is in the slideshow,
Professor Vivek.
we'll be able to completely see the slide, sir.
Professor
Sir.
Vivek.
Sorry, sir. Yes, sir. Tell me, sir.
Yeah, are you able to see it in slide mode or not?
No, sir. It's in normal mode only, sir. It's not in the presentation mode, sir.
Okay.
I think they are asking. I think presentation mode.
Is it okay now?
No, sir. No, sir. It is still slide mode only. Sir, slides. Sir, I think you are sharing only the PPT, sir. I think share the screen, sir. This presentation screen, sir.
Okay.
Maybe you stop.
Okay. Can you see it now? Hello.
It's fine, sir. Now fine.
Yes, sir.
Yes, sir.
Yes, sir.
Thank you. Okay, good. So we will see the behavior during the different weather condition like summer, winter, monsoon. We will see the morning, evening effect also, and we will see the region-wise profile also. And ultimately, the purpose of discussing it is the impact of the renewable, especially the solar integration, on the demand profile. And the renewable in terms of solar PV, it will affect the daytime profile only. So the daytime profile will convert to a shape called duck shape. How it will impact, and we will discuss it in the next slide. So this slide is showing the different region-wise profile. I'm at slide number 44. So you can see the western region profile is at the top, brown color, and the morning peak is higher than the evening peak because it's a very large industrial road, and that's how the pattern is different from other regions. Especially the northern region and eastern region, they have a typical evening high evening profile compared to the morning profile, and southern load is other. Now coming to the seasonal variation, we all know how do we use the energy. Like currently we are facing a winter season, and in the winter the morning peak is much higher than the evening peak, and then there is sudden fall in the night time. But in the summer time the evening peak is more than the morning peak. Similarly in monsoon the evening peak is more, and if we collect it, make an average all over India, yearly average, the profile looks like the last one. And there we have a morning peak and evening peak both, but the evening peak is much higher and much steeper also. It is 200 megawatt per minute kind of requirement is there. So the question arises here that from the system operator point of view, what is the problem with this kind of load profile? Does the system operator will have any problem with this load profile? Anybody please respond.
Sir, there is sudden changes in the energy demand, and that's why the generation will be very transient like that, sir.
So what is the problem? What is the does it this load profile is desired load profile by the system operator?
No, sir.
What is the desired load profile?
Approximately constant or small variations, sir.
Flat. Yeah, the flat demand is the desired load profile. So what is the problem with this peak?
More generation is required.
Let it be, we can supply more generation. So generation can be,
Generation
yeah.
has to be continuously varied according to the load pattern, sir.
Yeah, so generation will follow the load. That is what we generally do in the system operation. Generation follows the load.
Yeah, it would be needing more and more accurate data, more realistic data actually for
Load
plan.
forecasting, see, load forecasting is very dynamic thing. So there is always some kind of reserve is required to meet the fluctuation in demand. Okay, so even if you go for very accurate forecasting, you will never able to find accurate load in terms of generation. So you have to support it through some ancillary services with the spinning reserve, non-spinning reserve, and other kind of voltage and frequency support services. So my question is, what is the problem with this? Let it be whatever is required. Why this is not desirable? What is the harm with this?
So we cannot detect whether it is whether we can get the maximum load or minimum load at a particular time.
What whether I could not understand minimum maximum load?
So actually we need to know how much load at a particular time we need. By this we can't detect whether the load is minimum or maximum.
Why not? The
Because it
pattern
is a
is
variable, sudden
no, but
variable. So
variable, but pattern is known. More or less, pattern is known that when the morning peak will come, how much it will come, when the evening peak will come. It's a standard. Means see our own load profile, what we do, how do we use at our home. So it is almost similar every day.
The gap between this peak demand and installed capacity would be
So
high.
what is the problem with that?
Sir, at that time we have only the conventional. We don't have the non-conventional energy sources for the generation.
So it's difficult. So it's difficult to integrate basically solar and other renewable in the evening. Maybe this could be the reason.
Obviously, in the evening when sun is not there, what is the purpose of solar?
Yes,
solar will always be feeding the power whenever there is a sun.
yes.
See,
Unless
the problem
storage
here
is there.
Yeah, you see the evening peak. Evening peak is happening around between 7 to 8 p.m., right? And it is happening for a very short period of time. Right? Now to meet that peak demand, this is called a peak demand. You have to maintain the generation, transmission, distribution for full 24 hours. It is not that the generation and transmission and distribution will remain for only 1 hour. Rest 23 hours it does not require. Once it is created, it has to remain there for 24 hours. However, it will be used for very short period of time. So that will increase the cost of energy. Because your cost of energy includes the overall infrastructure. It's not for that and that's how the time of day tariff has come up. You know the TOD? Have you heard about TOD or TOU tariff? Time of day tariff? Anybody?
At the time of peak demand, the tariff would be higher than the.
Yeah. And so what are the other tariff called? Peak tariff, off-peak tariff, non-normal tariff. Do you have any idea what is the difference between peak tariff and off-peak tariff? How much it is different from these two values? Range of peak tariff and non off-peak tariff for residential consumer? Any idea? So it is almost double. So if you have a non-peak tariff is around 4 to 5 rupees, the peak tariff will be 9 to 10 rupees. Okay, and that is the purpose that to reduce this peak load. So once you pay more, you will reduce your own load, and that's how your peak shaving will happen. Those come under the demand side management. So these practices are performed through the demand side management. Okay, now coming to All India duck curve, expected All India duck curve that I was talking about. Now here you see in the daytime when there is a sun, so what will happen? The load will, the net load will be the actual demand minus PV generation. So the net load is shown as a downward valley and the actual demand is shown as a red color, which was the earlier curve. So the net load will be the actual demand minus PV generation. So PV will happen in the morning 6 o'clock or 8 o'clock to evening 6 o'clock. So because of that, the reverse of that means negative of that will cause a reduction in the load. So with the higher and higher penetration of solar, what will happen? In spite of the flat load profile, you are getting a downward ramp in the morning time, as well as your evening ramp is increased. It has longer period of time and for a longer ramp also. So the desired load profile by the system operator was a flat one, but with the renewable integration, what we are getting an additional downward ramp in the morning as well as increased evening ramp, and that is causing further challenge for the system operator. And you can see the curve looks like a duck, and this is the belly of the duck. So higher and higher PV penetration, belly will go down and down. Are you following it?
Yes, sir.
Yeah. Any question here? Okay.
Sir, can you just discuss the scenario between this 8 a.m. to maybe this 6 p.m. Yeah, the middle one.
Yeah. So 8 a.m. to 6 p.m. Right. Now, in the morning when the solar PV generation will increase, the net load, which is actual demand minus solar PV generation. Okay. So what will happen? The net as go with the peak of solar in the noon time, more and more generation will increase. So net load will be down. Solar will with the actual demand. So this valley downward will increase as you have more and more PV generation. So the upper part you can see the year wise increase in the solar is expected, and the valley will increase more and more.
Sure.
Moving
Okay.
to do you have any question? What kind of storage we use in the power system? Any idea? In the bulk power system, what is the bulk storage system we use?
Sir, could you just repeat the question, please? The network connectivity.
What is the technology used for the bulk storage in the power system?
Capacitor, sir?
No. You just
Sir,
think
the
I'm coming back. I'm just joining back in 2 minutes. Just wait for 2 minutes. Yes. Hello.
Sir, the flywheel of the generator stores the energy.
Yeah, that is actually providing the inertia support, not storage. Bulk storage I'm talking about for hours. When we talk about the bulk storage, at megawatt scale, what
Batteries.
technology do we use?
Batteries.
No.
Grids.
Huh?
Grids. Power grids.
Power grid, I am talking about the storage for power grid. What technology is used for the storage in the power grid? Have you heard about PSP? Pumped storage plant?
Yes.
What is that?
It's mainly used in hydropower generation and
yeah, it is a hydropower generation technology only. And actually they used as a generation as well as load in a cyclic manner. Means they operate as a generator during the daytime and they operate as a load during the night time. Okay, so they operate the same hydro storage plant technology. They consume the energy and fill their reservoir of the water during the night time when tariff is low, and store the water at some reservoir that becomes the stored energy. And during the daytime when tariff is high, the storage is required. They generate the energy through that reservoir water and economically viable with that change in tariff. Nighttime the tariff is very low, in daytime tariff is high. So that's how they are feasible with the economically also. Right?
Okay, okay, sir. Okay, sir.
Yeah, 1 minute, please. Yeah. So now I am at slide number now at demand management through storage and EVs. So pumped hydro storage system is used not only in India, it is being used globally, and it is covering actually 99% of the worldwide storage capacity at the power system level, right? And as we know that intermittency and this variable nature and this evening RAM, morning RAM, all this is leading to the essential requirement of energy storage in the power system. Battery and all that are very costly technology still, and at bulk level it's not easy to use them. So energy storage is required for the grid flexibility and grid stability, which is done by the hydro storage plant. We have a pumped storage plant in West Bengal, which is in a place called Purulia, and it is one of the largest storage plant in India of 900 megawatt capacity. And you can see the bar shown for the blue and red color. Can you able to see this slide? Purulia PSP operation.
Yes, sir.
Yes, sir.
Okay. So in the upper half, it is showing the blue color bars, and the lower part is showing red color bars downward, negative energy. So this is when it is working as a pump to upload the water, and in the morning time, it will work as a generator to generate the energy. Now the electric vehicle is another source going to happen in a big way, because number of electric vehicles, a single electric vehicle may not be large enough to support the grid. But when we have thousands of electric vehicles at the same location, like a multi-story car parking lot, then it can help the network in a better way. The only challenge here is that their charging and discharging has to be coordinated. If they are not coordinated, that may lead to an adverse effect on the power system. So this electric vehicle charging and discharging timing, and when and how many number of vehicles are being charged or discharged at a place, that need to be in a time phased coordinated manner. So suppose in a daytime, when you suppose you are having an electric vehicle, so when you are supposed to start for a work, you are expecting your vehicle should be charged enough, right? So that will be discharged when you travel from your home to your workplace. And again, in the evening when you start from your workplace to home, you are again expecting to be charged state again. So at the workplace, you have to get it charged because you have discharged it while traveling in the morning. Now you want it to charge, right? So in your multi-story car parking lot, if you put it on charging, what will happen? The daytime valley which was going downward, it will reduce. So all those electric vehicles can be charged during the daytime when solar production is also there. So it should be parallel to the future solar production hours. Now in the evening time, again you will discharge it while traveling to the home. So again you will put it in the charging in the night time. So again night time there is a sudden dip. You can see in the duck curve there was a nozzle drop. You can see at the evening after 10 p.m. there is a sudden drop in the load, right? Which will not happen if such kind of load is there. So it will help to make the load balanced, as well as it will provide a vehicle to be charged also when the morning when you want to go to the workplace again, right? So that is the way it can be coordinated. It will, if you put large number of electric vehicles being charged at the same time, same place, the voltage fluctuation issues or the power line losses may also increase with that. So there are some many papers are available for coordinated charging, discharging of electric vehicles also. This is all about it. Now this is talking about the institutional framework of Indian power sector. So electricity is a concurrent subject. So we have at central government level as well as state government level, we have similar kind of organizations. Like we have power generating stations at central level also, at state level also. At state level, the transmission and distribution are unbundled. They are being separated, and that's what the restructuring is called. Then we have load dispatch center at state level, and at central level also we have regional load dispatch center as well as national load dispatch center. We have regulatory commission at state level as well as central level, appellate tribunal above that. We have a national power exchange, 2 power exchanges we have trading licenses which are also national in terms of their operation, and then R&D institutions at central level are there, state level are also there, Central Electricity Authority is there. So they all are integrated, and independent power producers, IPPs, are there at state level and central level also. They work together like this. So each state has one load dispatch center, and above that in a region there are certain number of states which govern through one regional load dispatch center, and above all there is one apex body for national load dispatch center for coordinated operation among the regional grids. Merging of various regions has happened over the last more than 30 years since 1991, and you can see the first 2 were synchronized was east and northeast. Then we synchronized the east and northeast with the west, and then northern grid was synchronized, and recently in 2013 the southern grid is also synchronized. So we have now one nation, one grid, one frequency. This is all evaluation. Now coming to the on a daily basis, what is the energy transaction takes place? Are you following my slide quickly?
Yes,
sir.
Okay, good. So now I'm talking about the inter-regional and cross-border exchange, and in a typical day, we have around more than 3,000 million units of energy transaction, over which the western region is highest, almost 30% goes there, and similarly southern region and northern region are second highest. Then eastern region is very small, 10% only, and then Northern region is only 1%. Okay, and then we have cross-border trading with the Nepal, Bhutan, and Bangladesh. Now recently with the Myanmar also. As I've told you in our generation plot, we have Bhutan import as a generation source continuous. So this is 1.75 million units is marked from importing from the Bhutan. Nepal and Bangladesh are the deficit countries. Nepal is also hydro based. Major source is hydro generation, but in Bangladesh is gas dominant resources, and they both are deficit. So most of the time in a year we export power to the Nepal and Bangladesh. Similarly, Myanmar also we have started recently. In our Indian boundaries, we extract the energy from eastern and northeastern region and export to the northern, western, and southern region, which are deficit regions. And this eastern and northeastern region has a pithead thermal power plants and hydro resources with 765 kilovolt ring system. This is the map for transmission network, and you can imagine the complexity. This is only for 400 kilovolt and above. If you go down further voltage level, the complexity will be more and more, and it has increased a lot over the last 70 years, as we have seen. Now we have lakhs of kilometers of transmission line available in India. So it's not only the generation growth is important, the network growth is equally important. Otherwise, system will not work. So over the last few years, the growth in transmission lines as well as the substation capacity is significant, which is in the range of transmission 7% and the transmission capacity of substation is 12% is known. Okay, so this was all about the within India. Now we talk about the cross-border power market with our neighbors, and our neighbors have very mostly common way of power production, like mostly are hydro dominant. However, we are only the source, basically the thermal or coal dominant in our neighbors, among our neighbors. Sri Lanka is actually the hydro dominant, and Sri Lanka is also hydro dominant. Bangladesh is only gas dominant, and you can see in terms of amount of energy or installed capacity, we are the highest, then followed by Pakistan and Bangladesh. This is, we have already discussed, per capita electricity consumption. The world average is more than 3,000, but ours is around 1,200 or 1,300, which is quite low compared to the world average. US is very high and second followed by China. These are the few important transmission lines, corridors, which are being used by for our cross-border power trading. Like with Nepal, we have 3 power transmission line, 2 from Bihar, 1 from UP. For Bhutan, we have 3 transmission line, all from Bangladesh. It's all from West Bengal, sorry. Then West Bengal has 1 line with the Bangladesh, and Tripura has another line with the Bangladesh. And through Manipur, we have a line through the Myanmar also. These cross-border transactions, mostly Power Trading Corporation, PTC, and NTPC Vidyut Vyapar Nigam, NVVN, are the 2 major power trading licensees are involved for this cross-border power trading. So in Bhutan, we import around 1400 megawatt, and from this Tala and Kurichu and Chukka, these 3 the transmission line which we have shown you in the previous slide. These all being managed by the PTC. NVVN is supplying 250 megawatt power from NTPC stations to Bangladesh, and they have a long-term contract also. And DVC is also involved for this Bangladesh power cross-border transaction. PTC is also supplying Bangladesh from the WBSCL and Meenakshi Power, and NVVN is supplying 150 megawatt to Nepal on the short-term basis. So overall, power trading is beneficial to enhance the various business opportunities within India and cross-border trading also. All the emergency situations can be met partially through the short-term market or power trading, and market development through healthy competition or market driven by cost determination. It is not that cost and price are the 2 different things. So it is cost determination. It is not price determination. The price can be anything beyond the cost, but cost is assumed to be actual cost, actual value of that product. So value filling by the long term for the long term contracts is also supported through the short term contracts or power trading, and it provides the competition among the stakeholders, and it also helps for the renewable integration. Renewable integration actually, I don't know how much of you are aware about the RECs. Have you heard about the renewable energy certificate, RECs? Anybody?
No, sir.
No.
Nobody heard about REC, renewable energy certificate. Have you heard about energy saving certificate, e-certs? I think all of you must keep updating yourself through the Ministry of Power website and this Power Exchange websites, because these things are available in our system for more than 10 years now. Okay, so you must be updated for that. And these things are also very important from the point of view of they are evolving. It is not that they just have stopped from where they have been. They are changing significantly, and they are evolving from their previous experience. And so in Power Exchange, if you go to their website, you will find 4 types of products actually, or 4 type of platforms, 4 type of market products available. One is called day ahead market. One day ahead market means that the market trading or the bidding and market clearing is done 1 day ahead than the actual scheduling. Then second, actual delivery. Second is related to the term ahead market. In term ahead market, real time market has also come just few hours before the actual delivery, and it can be done in advance for weekly basis also. It can be done on the when the day ahead market option is closed. So that provides all time range. Then third is the renewable energy certificate, RECs, and fourth is energy saving certificates, e-certs. E-certs are the recent one after the RECs. And initially they started with day ahead market, then added the term ahead market, then RECs was added, then energy saving certificates are added. So RECs are actually about talking about the renewable power generation. So what happens when what you say, renewable purchase obligation is also one thing which has actually promoted these RECs. So a few years back, when this each distribution company were asked to generate or were asked to use renewable generation as a certain percentage of their energy transaction. So that is an obligation because it was mandatory. So each distribution company has to manage or arrange certain percentage through the renewable generation. Now it may be possible that in that state the renewable resources are not good enough. So what they do, they are supposed to balance that obligation through the certificates. It is not mandatory for them to trade the physical delivery of electricity, right? So the equivalent one certificate is equivalent to 1 megawatt hour of renewable generation, renewable source generation energy, which they can trade through the power exchange. It is not sale and purchase; it is traded within certain price band, minimum and maximum. So the thing is, the problem was with the this renewable energy certificate is that it is based on the renewable purchase obligation. So they have to arrange certain percentage of their renewable in a percentage of their generation, their electricity transaction through the renewable generation. Okay, any question here? So I think this is the last slide, then we'll move to the next topic, then we'll take some questions. So overall, if you see our power system has grown up in a very peculiar way and very high growth rate, but still we have a shortage in terms of both peak demand megawatt and energy million units. And we have seen the federal structure, NLDC, RLDC, everything is there, but we have a decentralized scheduling and dispatch, means state level the scheduling is done also, and regional level also, Diversity in terms of resource, in terms of demand, and variation is also
becoming flat also.
So, any question here till? Yeah, our problem is different. Our population is our problem. If we reduce, if we start, if our population stop increasing, then the scenario will different. So ultimately, the resources are distributed among the population, and the cost will increase accordingly. The population is increasing, resource or technology may not increase in that proportion, so the cost will definitely increase.
Okay, thank you, sir.
Yeah. Okay, any other
one
question?
query, sir. Yes, sir.
Please.
So, is PMP the answer of this intermittency?
Pardon? I couldn't understand.
Pump storage plants.
PSP, yeah.
Is it the answer of intermittency of renewable energy resources?
Yes, it can be. It can be because nowadays, as I have told you, we are coming up with gigawatt scale solar plants, right? So, and at one place. So, at one place, 2 gigawatt plant, suddenly there is cloud comes. So, it will definitely impact the system performance, right? If it is 100 of kilowatt, then it may not impact the system performance at grid level. But it is a 2 gigawatt or 5 gigawatt kind of plant at one place and cloud comes, then there may be a situation. But those cloud intermittency issues are very, very short, right? The PSP is generally used for hourly purpose, the long term purpose, long storage or bulk storage level for longer duration. So these small intermittent things can be settled through AGC or LFC or inertia of the existing synchronous generators because the duration is very, very short in that intermittency issues.
Okay, sir.
Yeah, any other question? Okay,
and in your previous slide, you had mentioned floating frequency. What was that, sir?
Yeah, floating frequency is actually in our system. I don't know whether you have heard about it or not. Have you heard about unscheduled interchange UI mechanism or deviation settlement mechanism DSM?
No, sir.
Actually, that is a indigenous balancing mechanism we use in our system, DSM. So that actually based on frequency linked price vector. So when the system frequency is very low, that price of DSM is very high. So either the generating company or the consumer is penalized. Both supplier and beneficiary are penalized based on that price, right? If they deviate from their schedule. So that deviation is directly linked with the frequency. So our frequency, what do you say, the frequency range in which that DSM is defined is quite large, right? It is 48.5 to 50.2, and that has been narrowed down over the years based on the experience. But still, we have a very, very, you can say, longer range compared to the developed countries where the band of frequency variation is quite small, very, very small.
Okay.
Any other question?
And do we have this peak hour tariff and off peak hour tariff in some states? I guess it's not there in every state.
Yeah, it is different in different states because electricity is a concurrent subject. So it is not uniform everywhere, and it is not applicable everywhere also, is still not. So it is being developed, coming up. In West Bengal we have.
Okay, sir. Thank you. Okay.
Even in most of the states has actually. I have one slide where TOD implementation is given. Not in this presentation, but you can find out in what are the states where this has been implemented. And second thing is, in some state it has been implemented to the industrial consumers, not with the residential consumers. Okay.
Yeah. Thank you.
Okay, so let's move to the third part. Last part is hybrid AC/DC microgrid. And as the smart grid is the title of your program also, I have put few slides on smart grid, and the definition of smart grid maybe in inauguration session might be might be discussed. It is defined as a flexible, secure, cost-effective, decarbonized power system. So what do you mean by flexibility in power system? Flexibility is nothing but the absorbing power or absorbing capacity with the change in generation, change in demand, or any such disturbance actually. Secure means it has to remain within the operating conditions. Then cost effective, it should not be. See, one madam was saying the cost is increasing day by day. So nowadays we have to understand what we are paying for any commodity is, does it have the worth or not. So we don't expect that electricity will get cheaper anytime, right? We should understand the value, the worth of the electricity. Can we sacrifice 2 hours or 4 hours a day and you will accept for low price of electricity? No, you don't want. You say, no, I need 24 hours electricity supply, right? I am ready to pay for it because it is worthy for you. Most of the things are depends on electricity. So you don't see the electricity just for the it is giving you lighting or some other appliances, but most of the gadgets, most of the things are depends on it. Similarly, decarbonized power system, the carbon emission norms are very strict nowadays. All are obligated to meet those obligations. So smart grid is also helping in that. Wide extensive use of ICT. Then the distribution network, what we were having was passive in nature, unidirectional power flow, which is becoming active in nature because the sources are being connected in the distributed network. And demand side participation through the controllable load like electric vehicle, heat pump. Then intelligently integrate the action of all the users. The consumer is becoming prosumer because it is producing also sometimes. So it is producing as well as consuming. So the name is given prosumer. Finally, we have to deliver sustainable, economic and secure electricity in an efficient manner. So that is all being considered under the smart grid. And you can imagine a system like this where we have a lot of sensors involved, a lot of processes involved to maintain the status of the network. And any emergency or contingency situation arises, and it will take appropriate control action also, where we can have a centralized plant, we can have an industrial load, we can have a storage, we can have wind, solar at the rooftop, we can have a microgrid, which can operate in both grid connected standalone mode, and demand side management as well as smart appliances. So you know all that you can now through your mobile smartphone, you can control your home appliances also from remotely from your office or wherever. But for that you need a network. So your home also should have a proper network, internet facility. Your mobile should have a good telecom network. So all that will lead to this kind of situation. Now, this is the actual setup that we have developed at our institute, IT Kharagpur, which is a hybrid AC/DC microgrid facility. And if you remember, the initial figure is more or less similar to that, but here the actual pictures are shown for the different type of sources. So in the AC microgrid, we are using crystalline solar PV cells, 3 different type of solar PV: monocrystalline, polycrystalline, and quasi-mono. And all 3 are connected with different type of inverters also, like monocrystalline is connected with the grid tie inverter, 510 kilowatt, 2 units of 5 each. Polycrystalline is connected with the micro inverters. We are using 250 watt, 40 number of micro inverters. So each inverter is connected with a single panel. Then we have a bidirectional hybrid inverter, which is again 10 kilowatt of size. And all these are connected on the AC microgrid bus with a wind turbine, emulator and generator system. We have a diesel generator also. We have a programmable electronic load with the actual building load. Then on the DC side, the lower side, we have a solar PV, again thin film type of technology, amorphous silicon and CIGS PV. And both of them are connected to the DC microgrid bus at 380 volt through their buck converter, DC-DC buck converter. We have a multi-storage system also. We have fuel cell system of 10 kilowatt. We have supercapacitor bank. We have a lead acid battery bank. We have programmable electronic load. All are connected on DC microgrid. And we have a interlinking converter of 20 kVA between AC microgrid and DC microgrid. And the whole microgrid is connected with the main grid, utility AC grid at 415 volt. There is a 100 kilowatt plant also, the part of the project at one of the hostel rooftop. However, in our campus, we have a 1.2 megawatt PV installation already done, and another 1 megawatt installation has started. And we have a dotted line showing the Ethernet communication for taking the signal and giving the control signal to the individual converters. So these are the various lab facilities created under this system. We have the topmost left side, the upper row. The first figure is showing the control room where we have a microgrid control center where we can have developed the GUI, lab view based GUI to monitor the system and give the control signal also. Then the second in the top row is the blue color lab, which is having the multiple storage, battery, supercapacitor, fuel cell together. Then we have a rooftop PV installation with single access tracking system. We are using different type of tracking also. The single access tracking, we have using dual access tracking. Just below that figure is a dual access tracking. Then in the right side most on the top line is the fuel cell system. We have an on-site hydrogen generation with the fuel cell. And 1500 liter hydrogen tank with electrolyzer and water tank is shown here, and 10 kilowatt fuel cell system. Then the middle row left hand side is showing two blue color machines, which are actually one is W-fed induction motor and another is W-fed induction generator. The motor is used as a wind turbine emulator here. Then we have a middle line, we have a supercapacitor bank, we have a rooftop PV installation with dual access tracking system, we have a inverter rooms with grid tie inverter, bidirectional hybrid inverter. Micro inverters are connected at the roof itself. Then we have a bus interface panel for microgrid and AC, DC and main grid. We have a battery system together. We have hostel rooftop installation, we have diesel generator. So all these facilities are used to make various studies for various projects which have been, some of them have been completed, some of them are still running, and it will also, these discussions will also help you to develop your own research ideas also. Any question till here?
Hello, sir. I'm Balaji from Tamil Nadu, sir.
Yeah, please.
Actually, the solar park project is government is planned for building for upcoming years. Solar park project. How
Yes.
the demand for daytime and nighttime how you manage? If solar park projects are built for around 500 megawatts, for daytime it will be working properly. But nighttime is how the demand will be managed.
Demand is managed by some other sources like thermal or hydro or whatever, nuclear.
Actually, the bulk amount of 500 megawatts generation is very difficult to manage. Daytime must be not having that much of power required, but nighttime it will be how much they compensate, sir.
500 megawatt is not a big amount. It's a very small amount. We have a 360 gigawatt PV total installation. No? So 500 megawatt is very small.
So around
the load balancing is done. Suppose you have a curve. You draw any hypothetical curve as a load curve, right? Now that curve will be have some rise and fall and like that. So the bottom part, the base part of the load, that is called the base load, is fed by the
load, peak load.
Yeah. So the base load is
in base load or peak load, sir? The solar project this will be used for base load or peak load, sir?
Yeah, so base load is fed by the thermal power plants, especially.
Okay.
Okay. Then thermal as well as nuclear, which are supposed to operate continuously 24 hours. Okay. And then the pancaking is made with the other sources which are available for a certain period of time, like that. And then finally, when you have a difference between your generation and your demand, those are filled up by the short-term market. Okay.
Okay. Good. Thank you, sir.
Yeah. Any other question?
Yes, sir. Sir, could you elaborate something more about this integration of microgrid into grid at IIT Kharagpur? The line diagram you just shown to us in previous slide.
Yeah,
Yes,
this
sir.
one.
So, yes, sir. Yes, sir.
So what do you want to know?
That integration of this microgrid with the this grid, sir.
Integration of
utility
microgrid
grids with the utility AC grid. Yes, sir.
Yeah.
Yes, sir.
So it is done at the, we have actually in our IIT Kharagpur campus is a bulk consumer. We are connected with the WB SCDCL, the distribution company, at 33 kV. Right. And from that 33 kV, we have a ring main system in our campus of 11 kV substations. We have 14 substations in our campus. And these substations convert that 11 kV to 415 volt, right? And this microgrid is connected to substation 13.
At 415 volt level. Okay.
Yeah, at 415 volt level. So the AC microgrid is at 415 volt and DC microgrid is at 380 volt.
Okay.
Right. And we can exchange the power through the microgrids, through this interlinking converter also, and we can get it isolated also. I will show you some more pictures about the communication and control of this microgrid when we talk about the last section.
Okay, sir. Yes.
Any other question, anyone? Okay. Now let's talk about. Yeah. Hello. Hello. Okay. So these are the few typical case studies which we have recently done or which we are undergoing by my PhD students. So first one is the real-time communication in hybrid AC/DC microgrid system using common information model. Now this common information model is actually required when what is the challenge we have during this developing this facility here. We need to purchase different converters from different manufacturers. Now, suppose, for example, I have bidirectional converters for battery as well as bidirectional converter for supercapacitors. But the voltage range for the supercapacitor is quite different from the voltage range of the battery system. And the DC bus is same for both of them. So we need to purchase different bidirectional converters of different ratings, because the voltage boost was quite large in supercapacitor from 50 volt to 380 volt. However, in battery it was 220 volt to 380 volt. Therefore, the one single bidirectional converter was not good enough for the supercapacitor. We have to go for four units in cascaded form. Similarly, the fuel cell is a unidirectional converter, which is only boosting the voltage from 48 volt to 380 volt, and it is unidirectional. So when we connect all these converters and try to communicate with them, we face some problem in terms of communication, and that leads to this common information model. So we'll talk about it in detail in the next slide. Then second is comprehensive performance evaluation of various solar PV system configurations. Here what I have shown you already that we have used different type of PV technology, crystalline and thin film. We have used different type of solar tracking system. So we have made 4 different such combinations with the centralized inverter and micro inverters also. And we simulated the whole system, as well as we have we have measured the experimental data also, the performance data. And then we evaluated them based on the technical index as well as the economical index, and compare the four different system configurations. And we have recently published a paper on that also in IET journal. Then we have a unified distributed control strategy for DC microgrid with hybrid energy storage devices. And here we have developed use this battery and fuel cell and supercapacitor together for control of DC microgrid. Right now we have one Indo-UK project where we are working on this low voltage fault ride through facility for solar PV system. So again, we are using the storage device to develop this fault ride through facility for solar PV inverter system. Then one recent PhD student has completed these last two work on intelligent control for hybrid energy storage system and standalone DC microgrid, as well as power flow control and sharing between interconnected multi-microgrid systems. So we'll talk about them one by one. So about this first one, the common information model, the same system what I've shown you, I've shown it in a different form to clarify the communication and control layout. So the top layer is showing the rooftop arrangement, and the rooftop we have solar PV installation, and one unit of 10 kilowatt is having the microinverter at the rooftop itself. Then at the top floor of the building, third floor, is having this inverter room where all these inverters are placed in a one room. Not only inverters, this DC-DC converters also for DC microgrid side. And there is a local controller which is feeding the data from that DC-DC converters, and these inverters are provided through API keys directly to the GUI. So this central GUI is developed in microgrid control center, where the supervisory controller as well as real-time controller from OpenRT are installed. Then we have a programmable electronic load also in that floor. And then first floor and second floor there is nothing. Then in the ground floor of the building we have one side we have this wind turbine emulator and generator system along with interface grid interface panel. And then one building is there outside, just outside the building, with this multiple storage system of fuel cell, battery and supercapacitor, as well as this electronic load. So you can see there are different dotted lines are shown for different type of data transfer. The legends are given at the right corner. So data transfer through serial port, data transfer through IOs, data transfer through Ethernet, and the full complete line is shown for the electrical connection. So you can imagine that different type of data is used for different type of converters, interface basically, power electronic interface, and they are talking to the local controllers. Then local controller is communicating with the central GUI and supervisory controller and real-time simulator. This is the GUI which is based on common information model. So common information model based GUI is shown in this picture. You can see there near the source there is a small box, like near the battery you can see there is a voltage is indicated here. Similarly for the PV at the right top you can see the three gray boxes are shown, which is showing the power output at a particular instant of time. So you can see the status of storage, status of sources which are connected to the system, and you can remotely control the network connection also. So there are a lot of normally open, normally closed switches are there, along with the automatic relay switch. Green and red signals are shown, indicating the on and off situation for them. So it was a part of a project called Reconfigurable Distribution Network. So this is all being developed under that project. This is the DC microgrid part, where central part you can say the NI stereo local controller is there, and the right hand side bottom there are 4 different converters for the supercapacitor. Then battery converter is there, and we need to convert the communication type like RS485 to USB. Then because NI stereo is connecting with the USB only, so all these changes has to be made and to make it compatible with the controller and converter. And fuel cell is talking to the local controller through the current output module, and this electronic load, and then finally talking to the LabVIEW GUI and the microgrid control center. This is the paper where the second work of comprehensive performance evaluation is published, where we have used these 4 different type of configurations. One is a fixed structure, fixed axis structure connected with a central inverter. Then we have a dual axis sun tracking structure connected with the central inverter. Then we have a fixed axis structure connected with the micro inverter. And the fourth one is a dual axis sun tracking structure connected with the micro inverters. So here we found that the microinverter system with the dual axis sun tracking structure gives the best technical performance. However, the cost with the microinverters was slightly higher, and economically the dual axis sun tracking system with central inverter is most favorable. So these are the various index which are being compared with the experimental data and the simulation data, like monthly energy yield for one full year of 2017-18. Then performance ratio over the year, and for all the 4 configurations. And this is the net present value for economic evaluation. This is the levelized cost of energy for different degradation rate and the interest rate has been compared for all 4 configurations. This is about the distribution control strategy for using the hybrid energy storage devices. So we have supercapacitor, we have battery, we have fuel cell, and different modes for different bus voltage has been considered when the storage devices are available or not available. Then this is the setup for the experimental study of DC microgrid. So what we did, we have different converters for the supercapacitor. So we divided the supercapacitor in 2 different banks, and we made the primary bank and secondary bank kind of strategy to control the DC microgrid bus voltage at 380 volt. And we have done this experimental study for this is the LabVIEW experimental output for the through the NI-CDO Ethernet connection, and the system which we have used is from our lab only. This is the setup for the fault right through study. And here we are proposing a storage device to be connected the DC bus of the solar PV inverter. So solar PV inverter is the 2 stage. One is the DC-DC converter as the inverter stage. In between there is a DC bus through which the energy storage device can be connected. So based upon the fault and its duration, the amount of energy which will not able to inject from the PV to the grid will be stored in the storage device. That is the idea behind it. So for that we need a lot of measurement and a lot of control signal, and all that control strategy is being used here. And this work is still going on. It is not yet completed. And so there are various case studies. Test conditions have been studied. Case 1, when the operation in the dynamic reactive power support is required. And recently in Indian Grid Code also has been published for this fault right through operation with the solar PV. Earlier there was with the wind only. Now it is available for the solar PV also. So assuming that Indian Grid Code condition, how best we can design the fault right through facility. This is all being tested in the various conditions, operating conditions of the grid, X/R ratio and short circuit ratio. And this is the last one about the multi-microgrid system, the power flow control and sharing between the integrated multi-microgrid system, where we can see microgrid 1 is on the left hand side and microgrid 2 on the right hand side is shown. With they are interconnected through a bidirectional converter, and each microgrid is having its own source, storage, and load. Different type of storage being used. Like in microgrid 2, we have both supercapacitor and fuel cell along with the battery. Here it is only battery in the microgrid 1. And these are the case studies being done where we have shown the comparison between the this FLC and adaptive FLC, fuzzy logic control. Adaptive fuzzy logic control and fuzzy logic control algorithms are compared for different operating conditions. And it is shown that adaptive fuzzy logic control, actually adaptive fuzzy logic control is supposed to consider the state of charge of the all storage devices involved in the system. Our fuzzy logic controller is only considering the primary storage bank. and that is the difference, and that's how the performance is better with the adaptive physiologic control. And this is the simulation setup being used for this multi-microgrid system. Another multi-microgrid system where 2 AC microgrids are considered, and in AC microgrid 2 we have 2 DC microgrids 1 and 2. Here actually the idea is this work is also recently published in EPES, Electric Power and Energy Systems, and here we have considered 4 different type of converters and their control also, like the PQ control or VF control or VDCQ control, and we have shown the different scenarios of the PV, of the storage and the load in the grid also, grid import, export, standalone, all scenarios are considered and which are being simulated. So it's a simulation exercise. No experimental study has been done with this logic. All 4 modes of operation are shown here: M1, M2, M3, M4, and that is desired operating conditions are obtained. So now I am summarizing the whole presentation, and as we have discussed that to take the benefit of the large amount of dispersed renewables, their integration is necessary, and we need to utilize, because we have to complete our obligation related to the carbon emission, related to the environmental pollution. So that's why the renewable integration is must. We have to do that. Then existing grid with a large amount of conventional sources has to accommodate these renewable sources, and the challenge is that these renewable sources are increasing in their share, but the supporting services, which are called ancillary services, I don't know whether you understand ancillary services or not. Basically, they are supportive services like voltage support, frequency support, your spinning reserve, non-spinning reserve, drag start capability, all those comes under the ancillary services. So they were supposed to be provided by conventional sources, but now it is being asked by the renewable sources also to provide these services, right? And very soon we will also have a market for ancillary services. Right now our market is for only energy. We will have ancillary service market also. In developed countries, there are various markets: energy market, capacity market, ancillary service market. New types of storage technologies needed for uncertainty management and stable grid operation. So it is not only the battery will able to support everything. We have to develop new storage technologies, and ICT is definitely important for a smart or intelligent grid. And as I mentioned you that our stable passive distribution network with unidirectional power flow is converting to active distribution network with bidirectional power flow, and that is also calling different challenges, especially with respect to protection, because the distribution network was not designed for it. It was designed for passive and unidirectional power flow, but now with these changes, there will be many issues, especially with respect to protection. And India, we have different initiatives are going on and in a big scale to achieve this smart grid objectives. So that was all about. I'm thankful to the organizers, and thank you.
Sir, thank you, sir, for your wonderful session.
Thank you very much.
This session is really very interactive, and I think participants also got effective information out of this presentation, sir.
Yeah.
Participants, if you have any doubts, you can have an you can talk to sir.
So this picture is very unique. What is unique about this picture? This is giving you a electrical map. Actually, the electrical what do you say, the per capita electricity consumption indication. I got it from the earlier chief executive officer of POSOCO, Mr. Suni, and this picture is really unique. So I always use it as a thank you slide to just to give you an idea that which country is having. So you can see the white dots are shown in certain part of the countries. That white dot are showing the actually electrical consumption as dense it is, high consumption is there.
It doesn't have the data of China.
See, China is actually located mostly in the western coast, eastern coast of it. The rest of the part is landmass is not being really occupied, really dense enough. So that part is not that illuminated compared to like India. You say that white dots are available all over the India, almost.
Yes, sir.